Hello wonderful people, this video is all about electricity, as the name suggests, so this is specific for AQA. And don't forget I've done loads of other videos about forces and waves and everything, so have a look on YouTube, make sure you subscribe, and also have a look at the website A-Level Physics Online to find everything you need to help prepare for your exams. Now let's start with some of the basics. Now some of this will be revision of what you did at GCSE, and there are three quantities which we're really interested in. We've got V, I, and R. So let's maybe just consider a normal component from an electrical circuit. We're just talking about DC circuits at the moment. Maybe we have a resistor. Now, in this resistor, there might be a current. And this current is the rate of flow of charged particles. Now we use I for current, the intensity of current, the quantity of charge, and then we've just got our time over here. Now a lot of the time when we've got electrical circuits we're thinking about electrons as the charge carriers, but we could have ions in a solution, perhaps like chlorine or so on. The other thing about this is our conventional current, which we say goes from positive to negative. But the actual particles moving in a normal DC circuit are electrons, which are moving from the negative side and they're being attracted towards the positive end of the terminal. So conventional current goes from positive to negative, but the charge carries the electrons go the other way around that circuit. But what's actually causing this current to be there in the first place? Well, there must be a difference in the electrical potential from one end to the other. And this V over here stands for our potential difference. And although we often use the word voltage, it's probably better to say potential difference. And this is equal to the energy transferred per unit charge. So this is really what it is. It's basically the amount of energy that's being transferred by each charge carrier. So we can use W for the energy transferred and Q as that charge. So this is our definition of potential difference. Now, we might have a potential difference across this component. There might be a current flowing. And actually what we might find is that the size of the current that we can measure depends upon the size of the potential difference. A bigger potential difference, a bigger current. But there's something which is kind of resisting its motion, and that's what we call the resistance. And when it comes to the resistance, we actually define it as the ratio of the potential difference across a component divided by the current in that component. And again, we measure our resistance in ohms, we measure current in amps, potential difference in volts, and we measure our charge in coulombs. And so far we've just looked at a basic thing like a resistor, but actually what we're often interested in is how the current and the potential difference vary when we have different electrical components, and we call these the characteristics. Now to investigate these characteristics we need a simple circuit. I'm just going to draw mine freehand, so we have our source of EMF, so this is maybe a cell. We've got a switch because we don't want to leave the circuit on too long, so we don't want any overheating. And basically there are two types of circuits that we can set up. Actually, I'm going to come back to that one. Something that you might have done at GCSE is a circuit that looks like this. We have an ammeter that we use to measure the current inside that component. This is a component that we're testing, so it might be a resistor like we had up here. And across this resistor, we put in our voltmeter. And this is measuring the difference in the electrical potential between 2 points. It's measuring our potential difference. We have something to vary the size of the current and the potential difference. In this case, we might be using a variable resistor. So that's our resistor with an arrow through it. And this is one circuit that we can use to investigate that component there. But there's another circuit we can use, which sometimes is actually a little bit better. And this is using a potential divider circuit, which we're going to talk a lot more about later on. So this is my potential divider. On this loop we have an ammeter that again goes to the component that we're looking at. Across the component we have our voltmeter to measure the potential difference. And then this part here I've just drawn with an arrow, and effectively this means that we could move this backwards and forwards to vary the potential difference across this component. We're effectively dividing the potential using this component here, and this is a really good circuit because it means that you can vary it so the current actually gets down to zero. With this one over here, even if you set that to zero, there'd still be some current flowing. So this one is a better way to get a full set of readings. But what readings are we talking about? Well, what we do is we maybe take some readings, and we might look at how the current I and the potential difference are linked. And this is why we call it the IV characteristics. Now what we might find is that if you just have a piece of wire, or perhaps you have a resistor, we get a relationship a bit like this. As you have a greater potential difference across the component, we get a greater current flow. And what we might find is we get this straight line that goes to the origin. Now this could be for a piece of metal at a constant temperature, or it could be for a resistor. And the other thing that we can do is we can also have negative values of current, just like we had positive values, and negative values of potential difference, just like we had positive values over here. Now, this is the current IV characteristic for a resistor. And actually what we can say is that for any ohmic conductor, we can say that the current is proportional to the potential difference, provided there are constant physical conditions. This means that the temperature stays the same. Now it might be that you had maybe a different material, or in this case maybe a different resistor, and we might find that we get a different shape. Again, it's going to be a straight line going through the origin. And these two things here obey Ohm's law. And Ohm's law just says that the current is proportional to the potential difference. In actual fact, this component here, or this piece of wire, actually has a different resistance to this one. Now again, we've seen up here that resistance equals V over I. And that means if you wanted to work out the resistance, what you need to do to work it out is you take a value of V and you divide it by a value of I to get the resistance. What's important is that a lot of the time the resistance is not equal to 1 divided by the gradient. Okay, it might be in this case if you've got an ohmic conductor, but when we're looking at what happens with filament lamps and diodes, the resistance is not equal to 1 over the gradient. So this is very much what you get with a resistor. We also have filament lamps, and these have a wire inside which when it heats up it gives out light. Again, this one here, it's not going to be a constant temperature, and therefore this is not acting as an ohmic conductor at this time. And actually what we find is we get a shape like this. And this is really why it's important to say that the resistance isn't equal to 1 over the gradient. If you wanted to work out the resistance at any point, you take your value of V, you look at your value of I, and if you look at kind of effectively this value divided by this value, it's not the same as a gradient, which is at a different angle. So this is the characteristic for a filament lamp. And the other one that you need to know about is for a diode. So diodes look a bit like these, not particularly amazing looking, but these are really useful in lots of different circuits. And when you have a diode, it allows the current to flow in one direction but not the other. So one direction, there's no current, and then in the other direction we get something like this. And the idea here is that when you've got this part of the graph here, we have a very, very low resistance. So that's the IV characteristics for a diode. Again, this is hopefully just revision of what you did at GCSE. Now, if you have a piece of wire and you really want to measure the resistance in that piece of wire, it depends upon the length. If you've got something twice as long, it's going to have twice the resistance. And this is because there's kind of more things for those electrons that they might kind of collide with as they go along the wire. But if we had a thicker wire, so it had a bigger cross-sectional area, there's then more pathways for the charge carriers to move. And what we find is that the resistance depends upon the length, it's proportional to the length, but it's inversely proportional to the cross-sectional area. And the constant of proportionality we have is ρ. And what we can write is that ρ is equal to Ra divided by L. So this is a material property called resistivity. So resistivity, symbol ρ, is a material property, and it means that if we knew things like the area of that wire and the length, we could work out the resistance. Now for this one here, when we actually work out the area, we're often talking about wires which are circular in cross-section, and we can't always just use pi r squared because we actually measure the diameter using some kind of micrometer. And therefore you've got to remember that the area is going to be equal to pi d squared divided by 4, or you could just do pi r squared, but that's something that people maybe sometimes forget about. Now this value of resistivity, just like the resistance, it depends upon the temperature. And if we were to look at a piece of wire like this, what we'd find is that as the temperature increases, the resistance also increases. So why is that? Well, it's due to the free electrons and the vibrating lattice inside. So within a good conductor, we have lots of free electrons which are delocalized from the now positive metal ions. Now, when everything is quite cool, these aren't really moving around much. Remember, this is just stuff about how solids behave inside. So we have, basically when something is quite cool, the lattice is vibrating and it's quite easy for the charge carriers to move through. So something with a relatively low resistance. As something gets hotter though, these start to vibrate more and therefore it's harder for the electrons to move through. Often the reason this is actually getting hotter is because of collisions between the current, which is moving through, or as all these electrons are moving from one end to the other, these highly energetic electrons are colliding with a metal lattice, causing it to vibrate more. So what we find is that with most materials, when they get hotter, there are more vibrations and therefore it's harder for the electrons to move through, and therefore we have a higher resistance. But sometimes we have things where they are semiconductors. Now with a semiconductor, we can think of it a bit like this. We've got something where there are maybe electrons which are kind of bonded to the material. And when it gets hotter, there's enough energy for these electrons to then move out of that material. So when you have something where the temperature increases, there are more charge carriers liberated, and that means it's easier for a current to flow. So what we have here is something where as you get a hotter temperature, the resistance decreases. And this thing over here is a thermistor. It's a thermal resistor. And we can basically see how as the temperature increases, the resistance decreases. Often you'll be given a graph where you have to read some data, and actually sometimes you might find there's different thermistors that have different properties at different temperatures. So this one here is a negative temperature coefficient because as we go to a bigger temperature, the resistance gets less, as opposed to normal wire, which is going to look a bit like this. But there's going to be a point where actually, as something gets cooler and cooler, the vibrations of these particles gets less and less. And we get to a point where suddenly the resistance massively drops off. And below this temperature, there is zero resistance. And this is where we have superconductivity. This happens at a critical temperature. And below this critical temperature, the resistance falls to zero. And that means that we can have really, really high currents. That's really useful because we can then use high currents to have strong magnetic fields. And we can use this in all sorts of things, including MRI machines. So critical temperature, below that, the resistance drops to zero, which is pretty cool. So that's a little bit about resistivity. So what we've looked at so far are some of the individual components. We've looked at maybe a couple of circuits, but now let's have a look at circuits in a bit more detail. Now in circuits, the usual rules of physics apply, and that means things like charge are conserved, and also energy is conserved. You know, we can't create or destroy energy, we just transfer it from one place to the other. Now a consequence of the fact that charge is conserved means if we had part of a circuit and we looked at the current that goes into that bit of the circuit, that's going to be the same as a current that moves out of that part of the circuit. And what we can say is that the sum of the currents into a junction is equal to the sum of the currents out of the junction. That's sometimes known as Kirchhoff's first law, although that's not actually mentioned in the AQA course. But basically, current in is equal to current out. When it comes to considering how energy is conserved, well, maybe let's look at a part of a circuit. We might think about the amount of energy transferred to the charge carriers and how that then is related to the energy which is transferred by the charge carriers. And what we can look at is EMF, and we can look at potential difference. Now we've seen over here that potential difference is defined as the work done per unit charge. And basically this is the energy transferred within a component. But we have something similar. The thing which is similar is EMF, and we're using a kind of curly E, a kind of epsilon here. And again, we can work that out by the energy per unit charge. But this is the energy transferred to the circuit by maybe a battery, whereas this is the energy transferred out by a component. So when we think about EMF, we're thinking about effectively the voltage of the battery or the cell, and this is the voltage across that component. And what we can say is that around any closed loop in a circuit, the sum of the EMFs is equal to the sum of the potential differences. So let's have a look at that in action. Now there are two main types of circuit. We've got series and parallel. Now we can't really get much more simple than that. Perhaps we've got a cell and two resistors, resistor 1 and resistor 2, or we can have them set up in parallel, again with a cell and two resistors, although these could be any components. Now, thinking about this one here, there's going to be, from this cell, there's going to be a current flowing. So this is our conventional current moving this way around. Now, from this law here, looking at conservation of charge, the current in here must be equal to the current out, which is equal to the current in and the current out. And therefore, in a series circuit, we have the same current everywhere. That's just something that you might have seen already, but it's because of this fact that we conserve charge. In this circuit over here, however, if we've got current coming into this junction here and then the Y is split in two directions, some of the current's going to go this way and some is going to go that way. Perhaps we had 10 amps in, we might have 4 amps here and 6 amps there. The actual size of that really depends upon the size of these resistors. So what we find in a parallel circuit is that current is split at a junction. But now we can think about what happens to the EMF. So let's imagine there's an EMF across that cell, and there's a potential difference across here and a potential difference across there. And we're going to have a perfect cell where the Y's have zero resistance. For this circuit here, following on from this law here, Kirchhoff's second law, we can say that the sum of the EMF is equal to the sum of the potential differences. So that is equal to V1 plus V2. So in this circuit here, we're splitting that, we're kind of sharing that potential difference. And actually this is called a potential divider circuit, just a really simple case. In this one here, we might have a loop at the top where we've got the EMF over here. We might think about this being a closed loop, where the EMF is equal to the sum of the potential differences. And therefore, in this case here, the EMF is equal to the value of V1, potential difference across this. And also the EMF is going to be equal to the potential difference across this number 2 over there. So that's why in a parallel circuit, we have the same potential difference across each loop. Now, as a consequence of sharing the potential difference but having the same current, we can actually look at the total resistance of this circuit. Now, for a series circuit, the total resistance is going to be equal to the sum of all the individual resistors. So maybe R1 plus R2 plus however many other resistors there might be. When it comes to looking at a circuit in parallel, well, actually we have more routes for that current to move through. So actually, if this had a resistance and this had a resistance, their combined resistance is going to be smaller than if we just had one component, because effectively there's more routes through. So if we want to look at the total resistance for a parallel circuit, that's equal to 1 over R1 plus 1 over R2 plus, and it just keeps going on for however many resistors we have. And the key thing here is that you've got to remember to take the reciprocal. Too often people do 1 over R1 plus 1 over R2 and they say that's equal to RT. Just don't forget that you've actually got to do 1 divided by this answer to get your final total resistance. And that's it in a really simple case. Obviously these will be kind of added, you might have loops with maybe parallel bits and added to series bits, and there's going to be some complicated things, but this is the basis. And all you need to do is you need to work around your circuit, just remembering that charge in equals the current in equals the current out. The sum of the EMFs equals the sum of the potential differences. Combine this with this equation over here that says V is equal to I times R, and they're the main equations that you need for looking at electric circuits. Well, I say they're the main ones. There's another one, and this is to do with the power that a component actually dissipates. So how much energy is transferred from that component per second. We can work this out by saying that P is equal to I times V. Effectively, the bigger the current, the bigger the potential difference, the more energy transferred per second. We can also see that V is equal to I times R, so we can replace the V term with I and R to say that the power is also equal to I times IR, and therefore that's equal to I squared R, and the final one is that P is equal to V squared over R. Now you can use any one of these, you'll get the same answer. It just depends which raw data you've been given in that question. Now the other thing that you should remember from just general physics is that the power is the rate of energy transfer, so P equals E over T, and that means if we wanted to know the total energy transferred, we just multiply the power by the time. And it says here the power is equal to IV. So another equation which is sometimes really useful is that the total energy transferred by that component equals IV multiplied by T. So there's a lot of equations in this part of the course, but you've just got to sit down, memorise them, and actually then start to put them into practice by doing as many questions as possible. I mean, this hopefully makes sense, but when you see a real circuit question, it does get a little bit more challenging. Luckily though, in an exam, you don't actually have to make the circuit work, because that can be quite frustrating. All we're doing is we're applying a couple of equations to different parts of the circuit to find our final answer. Now we've got a couple of examples of potential divider circuits. This one here divides that potential difference between the two resistors. This one over here also divides that potential difference. And this is kind of an important category of circuits. So what we're going to look at now are potential dividers. And for these circuits, we have maybe a fixed power source, and then we have two resistors. So maybe here's a resistor, and here's another one. And depending on the relative size of this resistance to that resistance, that then tells us how we actually split the potential difference in this circuit. And what we might be doing is we might be measuring the potential difference across this resistor, or maybe this is set up to another thing, perhaps another light bulb, which when we get to the right value, the light bulb turns on. Now, this is really important because we can use this for a sensing circuit. So we might have a semiconductor, so we could have a thermistor, and as the temperature changes, that affects the resistance, which affects how much of that potential difference it actually takes, and therefore the potential difference across this bit of the circuit. We also might have a variable resistor, so we can actually adjust our circuit. And instead of having a thermistor, we could also have a light-dependent resistor. This is just another type of component where its resistance, rather than depending on the temperature, it depends upon the light intensity. So we might have an LDR. Again, you'll have seen these at GCSE. So this is one way that we can have a potential divider circuit. Some external change causes a resistance to change of one of these components, and that then affects how much potential difference is across it, which we can then use for something useful. Another way that we can draw this potential divider circuit is, again, we've got our fixed power source over here, and then we represent a potential divider with this kind of extra long resistor over here. And what we're interested in, again, is the potential difference between this point and some point within that resistor. And we draw it as an arrow pointing to that. And obviously this arrow could go effectively backwards and forwards. It's like a kind of sliding scale. When it's over here, then there's going to be no resistance, and therefore there's going to be no potential difference across this bit of the circuit. When we go to this bit, it's going to be at the maximum. So when you have a potential divider circuit like this, we can use the full range of potential differences available. So here are just a couple of examples of potential dividers. Now, the final bit of this course is kind of the bit which I think a lot of people find tricky, and that's looking at not only the electromotive force, but actually the internal resistance of a cell. And this is because in a real circuit we have stuff made out of actual stuff. We don't just have perfect wires. Inside this cell we have a load of chemicals, and therefore if the current is going to be moving through this, there's going to be some internal resistance. Now luckily this is quite small, but it's something that we can't ignore. So let's have a look at internal resistance. Now because this is often quite small, we can ignore it, and the question will say ignore internal resistance, or it'll direct you to actually take account of it. So let's think of a simple circuit. We might have a cell, maybe this one over here, and this is maybe connected to maybe an ammeter, so we can measure the current in that circuit. And we might have this connected to a resistor. Now this could be an actual resistor, or it could just represent the resistance of an external part of that circuit. And to show that there's some internal resistance, we have a small resistor that we put next to the cell. Sometimes you see it with like a dotted line drawn around it to show that that resistor there, it's not a physical resistor, but it's representing the internal resistance of that power supply. Now for this one over here, again, this curly E stands for the EMF, and this battery here says 9 volts. So this has got an EMF of 9 volts. It's a kind of theoretical maximum energy transferred per unit charge. But when we actually start to measure the potential difference of this when there's a current flowing, that internal resistance has an effect. And what we can say is that the EMF is equal to the current multiplied by R plus little r. Effectively, I times R is the potential difference across this component, and I times little r is the lost volts inside that cell. Now what we can do is we can do a bit of practical work, and we can measure the potential difference either across the external part of that circuit, or effectively this is the same as having that voltmeter across the terminals of the battery. And what we're actually measuring here, V, is our terminal PD. And effectively, as soon as we have a circuit where there's a current flowing, this terminal PdV is going to be less than the theoretical maximum EMF. In fact, we can draw this on a graph. And what we find is when we have a greater current flowing, we get less terminal PD. And that's because there's a current inside the cell as well, and that means this small resistance has a bigger effect. The value that we'd get on the y-intercept will be equal to the EMF. And also, because R equals V over I, the gradient here is going to be equal to a negative value of the internal resistance, which we assume is a constant. So internal resistance does have an effect. It might be that if you had a real circuit where we had a lot of cells in series, what we'd have to do is we'd have to add this internal resistance to that internal resistance to that internal resistance. So when you have cells in series, their internal resistances all add up, just like the total resistance of something in series just adds up and adds up and adds up. But sometimes if you had cells which maybe had some internal resistance, if you were to put them in parallel to one another, what we'd find is that depending on how many of these we had, because there's more paths for the current to move through, the more cells we had, each with an internal resistance, their combined internal resistance, the effect of that decreases. So with cells in series, the internal resistances all add up, but the internal resistances of cells in parallel would actually have less of an effect overall. Now hopefully this is a bit of revision about stuff that you currently know, and it's all very well knowing this, but it's down to you now to do as many practice problems as possible. So past exam papers, using your textbook. The more you apply these different equations, because there's quite a lot here, the more you'll realise that actually this area, this topic isn't too bad. Don't forget, of course, that if you haven't already done so, you can like the video, you can subscribe on YouTube, and also have a look at A-level physics online to really help you prepare for your exams which are coming up this summer. So thank you very much for watching, and goodbye.